Chapter 5, Volcanoes. The nature of volcanic eruptions. Factors determining the violence or explosiveness of a volcanic eruption are the composition of the magma, the temperature of the magma, and dissolved gases in the magma. The above three factors actually control the viscosity of a given magma, which in turn controls the nature of the eruption. Viscosity is a measure of a material's resistance to flow. For example, a higher viscosity materials flow with great difficulty. So factors affecting viscosity. Temperature. The hotter magmas are less viscous. Composition. The more silica content, the higher the viscosity. Okay, so felsic lavas, such as rhyolite, are much more viscous than basaltic or mafic magmas. Lower silica content, lower viscosity, or more fluid-like behavior, like our basalt. Dissolved gases. Gases expand within a magma as it nears Earth's surface due to decreasing pressure. The violence of the eruptions relate to how easily the gases escape from the magma. Okay, so more viscous magma, the harder the gases are for them to be able to escape. Okay, so fluid basaltic lavas generally produce quiet eruptions. High viscous lavas, rhyolitic or andesite, produce more explosive eruptions. Here's a Pahoehoe lava flow. So this is a basaltic magma that's gently flowing. It's not a violent eruption. Okay. Here's a typical Loa-A flow, also from basaltic magmas. So this is more chunky. It's still moving slow. Okay. Now, materials extruded from a volcano. Pyroclastic materials are fire fragments. The types of pyroclastic debris: we have ashes and dust, or fine glassy fragments. We have chunks of pumice, which is the porous rock from frothy lava. Lapilli are wallet-sized chunks of material. Cinders are pea-sized materials. Particles larger than lapilli, or larger than a walnut, are blocks, which are hardened or cooled lava, or bombs. They're ejected hot lava that cools while it's flying through the air, forming a nice aerodynamic shape. So hardened. So here, showing a volcanic ash to lapilli in size, very fine grain to coarse grain. Here's a microscopic view. So even the ash fragments still have the vesicles where gas had escaped. It's a picture of a streamlined volcanic bomb. It was extruded as hot lava, but it solidified while it's flying through the air. Okay. Features on a volcano. Openings at the summit of a volcano could be a crater, a steep wall depression at the summit, generally less than 1 kilometer in diameter. Calderas are a summit depression greater than 1 kilometer in diameter and produced by collapse following a massive eruption. Then vents. It's an opening connected to the magma chamber via a pipe. Types of volcanoes. Our shield volcanoes are broad, slightly dome-shaped, composed primarily of basaltic lava, generally covers large areas, and they're produced by mild eruptions of large volumes of lava. Mauna Loa in Hawaii is a great example of that. So here's Mauna Loa, a shield volcano. So it's a nice shield volcano with a shallow magma chamber. Okay. So this is in Hawaii. Cinder Cone, built from ejected lava, mainly cinder-sized fragments, so ejected lava fragments, cinders. Steep slope angle, rather small in size, frequently occur in groups. Here's a little diagram of a cinder cone. So this magma ejects as pyroclastic fragments that build up along the sides to form this cinder cone. Composite cone or stratovolcanoes are mostly adjacent to the Pacific Ocean. Examples like Mount Fujiyama and Mount St. Helens are large classic-shaped volcanoes, thousands of feet high, several miles wide at base, composed of interbedded lava flows and layers of pyroclastic debris. So here's Mount Fuji, this real classic composite volcano. Here's a diagram. So we have our conduit or pipe, we have our crater, we have some vents. Here's a parasitic cone that's built up around this vent. We have lava flows. And we also have pyroclastic debris being ejected. So this will be interbedded layers of lava and pyroclastic debris. Most composite cones have the most violent type of activity. For example, Mount Vesuvius. Also produce Nuit Ardents. These are fiery pyroclastic lava flows made of hot gases suffused with ash and other debris. They move down the slope of a volcano at speeds of up to 200 kilometers per hour. These may produce a lahar, which is a volcanic mud flow. Okay, so here's our Pyroclastic Flow flowing fast down the slope of that volcano. Here's some size comparisons. There's a shield volcano, Mauna Loa, nice large, slightly domed volcano. Here's Mount Rainier's Composite Cone, and then here's a little Cinder Cone. Calderas with steep wall depressions at the summit, generally exceeding 1 kilometer diameter. Pyroclastic flows again associated with felsic intermediate magmas, consist of ash, pumice, and other fragmental debris. Here's a classic caldera. This is Crater Lake in Oregon. This used to be the top of Mount Mazama, and it exploded a while back, and so much of the magma chamber emptied that it collapsed and formed this caldera. There is subsequent volcanic activity forming this little Cinder Cone volcano here, and precipitation has fallen and over time formed this lake, Crater Lake. Okay, back to pyroclastic flows. Materials propelled from the vent at very high speeds, for example, the Yellowstone Plateau. Fissure eruptions and lava plateaus. Fluid basalt lava is extruded from crustal fractures called fissures. The Columbia River Plateau, it's up in the Pacific Northwest, over time there were many basaltic flows that came off fissures, eruptions and fissures, and made layer upon layer of basaltic rock. So here's some of these layers of basaltic rock in the Columbia River Plateau. Lava domes. These are bulbous masses of congealed lava. Most are associated with explosive eruptions of gas-rich magma. After Mount St. Helens erupted in 1980, a lava dome formed within its crater. Okay, mostly made of obsidian. Volcanic pipes and necks. Pipes are short conduits that connect the magma chamber to the surface. Okay, so here's back Mount St. Helens. It exploded back in 1980, and here is this lava dome that formed as the last of the more viscous lava hardiness was coming out. Volcanic pipes and necks. Example, Shiprock, New Mexico. These are resistant vents left standing after erosion has removed the volcanic cone. So the magma is solidified in that vent. A nice resistant rock. And, oh, there's, that is not Shiprock, New Mexico. It's Mount St. Helens again. Okay, plate tectonics and igneous activity. Global distribution of igneous activity is not random. Most volcanoes are located within or near ocean basins at subduction zones. Basaltic rocks are common in both oceanic and continental settings, whereas granitic rocks are rarely found in the oceans. Okay, so here, basically a ring of fire right around the Pacific Ocean. This is where most of our volcanoes are found. So, igneous activity along plate margins. Spreading centers. The greatest volume of volcanic rock is produced along the oceanic ridge system. This is where lithosphere pulls apart. There's less pressure in the underlying rocks, resulting in partial melting of the mantle. Large quantities of basaltic magma are produced. At subduction zones, occur in conjunction with deep ocean trenches. Descending plate partially melts. Magma slowly moves upward. This rising magma form either an island arc, if it's in the ocean, or a volcanic arc if it's on a continental margin. Associated Pacific Ocean Basin, the region around the margin is known as a ring of fire. It's the world's most explosive volcanoes are found there. Now, intraplate volcanism, like in the middle of a plate, a tectonic plate, this is where we might have a plume of heat in the mantle, forms localized volcanic regions in the overlying plate called hotspot. This produced basaltic magma sources in ocean crust, like Hawaii and Iceland, but produces granitic magma sources in continental crust, such as Yellowstone National Park. So here's an interplate volcanism. Here's a convergent ocean plate boundary, a subduction zone, and here we have some partial melting going on and forming creation of a volcanic island arch anyways. That's it for this chapter.